Buongiorno, iniziamo la registrazione del the first part of our lecture of 18 November. Today we should speak about conditional probability, and this is something that we promised last time. Conditional probability is something that is very specific event. We know that for our probability space, we have a generic set omega. We have then algebra of subsets, and then we have also probability function. And therefore, in our set omega, this is our set omega, suppose that with some criteria, we have already determined a kind of event, that is some specific set A. Let us call it, as usually we are calling this set U. This kind of event that may happen, and for us the event is simply subset of our probability space omega that belongs to this algebra. Somehow we are interested in following phenomena to see probability of this event under the condition that some other event happened. Therefore, we have another event. Let us take this event here. This is the event V. And we want to see what is the probability that the event, the green event U happens under the condition that phi occurs. Roughly speaking, what does it mean? This is something very simple. This means that for sure we have to work with our domain V, and we have to see when V happens, how many times U happens. It is clear that first of all, we shall take this set V and we shall project on U. Therefore, we take only the part of green and red event. And you can see this part is simply intersection between U and V. When you intersect green and red part, the result is only this set that we can call intersected with V. Now, how we shall measure the probability that we have our event that is red and green when V happens. To be more precise, let us suppose that here we have n elements. Let us suppose that here the green one is with m elements, and the part of the intersection between U and V is formed by n elements. It is clear that to define the probability of U when the event V happens. This we call in this mathematical symbol probability of the event U when we have the condition that V happens. This simply, if we see what are all possibilities, for us all possibilities are when we have equidistributional probability space. We shall have to count how many elements of V we have. So this is M, all possible choices that V will happen, but among these all possible choices, the case when U happens also is measured by this number N. So we count the set U intersected with V, and we divide the set V. This is quite natural definition. This is our definition of this conditional probability. But you see, represent divide denominator and numerator by this N. We can write also that this is N divided by N. Tra mezz'oretta, chiedo scusa, ma ho iniziato? Sì, tra mezz'oretta, scusami. N divided by N, and we divide also the numerator M divided by N. As you can see, the numerator is simply the probability of U intersected with V, while denominator is simply the probability of V. So we can say that this conditional probability can be computed formally by these formulas, and as usual we have to take kind of example in order to understand this notion. For example, if we take
Professore, scusi.
Prego.
Io non ho capito il passaggio quando ha detto facciamo il determinante e poi è diviso per n. Scusi, mi sono...
Quale determinante?
Qui, no, definizione, scusi.
Questo non è determinante, questo è definizione.
Sì. E, non ho capito il passaggio dopo. Quando
Qui.
Cioè, perché
dividere numeratore e denominatore per la stessa cosa, per passare alla probabilità. Noi abbiamo che questa frazione è uguale a questa frazione, perché ha lo stesso n, numeratore e denominatore, ma questo adesso ha senso di probabilità, anche questo ha senso di probabilità. Quando lei prende A diviso a B e moltiplica numeratore e denominatore per lo stesso fattore, non cambia la frazione.
Sì, quindi l'abbiamo fatto per ottenere la probabilità. Per ottenere una probabilità, ok.
Abbiamo moltiplicato per 1 su n numeratore e denominatore.
Sì, ok.
Così numeratore diventa probabilità, denominatore diventa una probabilità ben nota. E possiamo dire che questa probabilità condizionata si calcola in questo modo, sapendo le due probabilità. Ok, adesso proviamo a vedere un esempio.
Scusi, professore,
Sì?
per cosa sta n?
Come?
Per cosa sta n? Sì.
Questo n sta per numero di tutti gli elementi dell'insieme omega. Grande insieme dove studiamo nostra probabilità. Qui ho notato omega ha numero di elementi n maiuscolo, U ha numero di elementi m piccolo, e qui l'intersezione U intersecato con V ha n elementi, ma n piccolo, qui n maiuscolo. È chiaro?
Sì, sì, grazie.
Ok. Ecco, l'esempio tipico è quello. We shall make some example. Probably I can do this example with the following. We know that, for example, let us make this example interpretation connected with example we started last time. If we have dice, so the example is connected with dice. We have two dice, and we make 2 times we draw these dice. We know that all exits can be measured as a couple, mn, where m is between 1 and 6, n is between 1 and 6. So let us take our event v. Our event v is, let us put with a red one, v, this event is simply m plus n is greater than 5. And let us take the event u shall be m is 3 or 4. Let's try to see what is our, first of all, what is our omega. Omega is the whole space of all results when you take 2 dice, two draws. Last time we computed omega. This is the set of all mn. Omega is the set of all mn such that m belongs to the set from 1 to 6, and the same is for n. Can you see well, or what is the resolution today? Is it satisfactory?
Yes, it's better.
Okay.
Could you read a little more bigger?
I shall try, because
Thank you.
I want to finish the example here and discuss. How many elements has omega? If we take all possible exits, last time we computed this. This was, what is cardinality of omega? When you draw 2 dice, how many exits you have?
36.
This is 6. things. Okay. How many elements has the set V? You can compute. Here I shall continue example 1, but I shall keep the main picture and of conditional probability. The example requires what is probability of U under the condition that V happens. If you know that sum is not bigger than 5, what is the probability of the event U? So let us compute what is cardinality of, let us use from now on only the black one, cardinality of U. Can you compute?
5.
M is 3 or 4. What is cardinality of U? Yes?
2.
Why? If M is 3, for example, N is free. Therefore, if M is, for example, starts with 3, how many possibilities? We have 2 dices. They are completely independent. Second choice, we have 6 possibilities. So in the second box, we have 6 possibilities. And then the other possibility is 4. So here we have other 6 possibilities. Totally, how many possibilities for this? If M is 3 or 4, the whole number of U is 12. As you can see, this is important. The green part of my picture eventually can be very big. We have to take only the intersection for our conditional probability, but have in mind that our event U can be really huge event. Let us compute V. How many elements has V? Let me try to ask you, what do you think? M plus N is smaller than 5.
Maybe 8.
Let us try to count. So what is admissible choice of M? Of course, not 6, not 5. Therefore, admissible choice of M is 1, 2, 3, 4. Because if M is 5, with any N from 1 to 6, we shall exceed. So if M is 1, how many possibilities we have for 1? So this is 1, 2, 3, and 4. So here we have how many choices? Possibilities, 4 possibilities. If we have 2, how many possibilities? Now we have 1, 2, 3. This is admissible, and 4 is not admissible. If this is 3, we have 1 and 2, and if this is 4, this is 1. And as you can see in the chat, Martina already suggested 1 plus 3 plus 2 plus 3 plus 4. 1 plus 2 plus 3, 4. What is the sum? Exactly what Martina suggested, 10. So this set has cardinality 10. Let us compute the intersection now. U intersecting. How many elements has the intersection and U and V? So what we need? M is 3 or 4. So if M is 3, what are the possibilities for our n? This is 1 and 2. So we have here two possibilities. If n is 4, we have only one possibility, 1. So totally intersection means two possibilities plus one possibility. This is 3. Actually, our initial formula was probability of the event u under the condition v happens is simply counted number of elements u intersected with v divided by number of elements of v. And we can, with this line here, simply apply the formula and deduce the probability of the event u under the condition that v occurs is exactly equal to 3 over 10. So we have probability 3 over 10. This is our conditional probability. If somebody posed the question, what is the probability of this exit, of this result, n plus n to be smaller than 5, when you know that the first dice is result is 3. Let me ask you if this example is clear, if you have some question. Of course, the calculation we did here was slightly, you simply divide 3 divided by 36 and 10 divided by 36. But you know, this is the same calculation. Can be simplified. You can use also probability of this, but also counting the cardinality of intersection and the cardinality of the set V, you obtain the same conditional probability, 3 over 10. Okay, again, small space for your questions. Of course, it is important to know, for example, the following thing, a relation between if the example is clear, I shall clean the first two lines to go further. If you haven't more questions. Of course, in this example, I think we arrived. I shall make small observation about the sum we have used in our calculation. 1 plus 2 plus 3 plus and so on, up to what is this sum? If in some exercise you need to compute this sum, it is important to know that this is always n times n plus 1 over 2. Or this is, let us check, Martina had 1 plus 2 plus 3 plus 4. 4 by 5 divided by 2 is exactly 10. So this is a rapid way to compute this infinite sum. Usually what you are doing, you take the first one and the last one, sum is n. 2 plus n minus 1 is again n plus 1. And you count how many times this appears. If n is even, this appears n over 2 times. And therefore, this is sufficient to prove this. Moreover, you can say that this is also binomial coefficient n plus 1 over 2, because we already computed binomial coefficients from the last time, and typically you can compute this sum using this relation. This is small observation to help you if you need to count more numbers, because you may have larger numbers, and therefore this is kind of help to do this. Now, what is the relation between P of U under the condition V and opposite? Because you know there are many events in which, for example, you know probability of this event under the condition V, and vice versa, probability of V under the condition of U. This relation, of course, can be computed, this connection can be computed very easy, and typically such type of relation simply requires one to use kind of more generic relation. Okay. Of course, here the relation is very simple. To obtain the relation, I shall clean 2 more lines. So we know that this is P of U intersected with V divided by P of V, while this is P of U intersected with V divided by probability of U. And if we take this probability here, we can say that the following relation is satisfied. Probability of V divided by probability of U. So if you know this conditional probability, and if you know probabilities of U, and you can compute the other probability using this relation. I think this is simply connected with the fact that if you take 1 second, P of V is vice versa. This is U and this is V. Let us check this relation. We know that this probability, conditional probability, is represented by this guy. So if I multiply by PU divided by PV, it is clear that PU with PU cancels, and we have PU intersected with V divided by PV. And this is exactly this conditional probability. Therefore, we have a relation that is given by this relation. And of course, if we have a concrete example, we can use this relation. Actually, our next step requires to have a kind of decomposition of our probability space. And in this case, we have to speak about formula di Bayes. This is simply gives us relations connected with some conditional probabilities. In order to represent these formulas, and then make an example. Again, I want to say that here we use always this discrete probability with events such that if you take event with one element, all sets with one element, they have the same probability. So we have equidistributional probabilities. Unfortunately, this type of probabilities, they are not typical, for example, for the developing of coronavirus probability. We know that there is kind of curves that are completely not uniform, so they have very strong jumps, and probabilities in this case are not redistributed. Somehow we are starting our probability study with simplest case. And our first step is to have our probability space omega that is practically decomposed as set uj. J starts from 1 to, for example, to n. What does it mean? This means our total set omega is decomposed U1, U2, disjoint sets. What does it mean? This means if you take U kappa, UL, intersection is always empty set when kappa is different from L. And therefore we have all our events, all our probability space, it is decomposed in such sets that of course belong to our algebra associated with omega. So in this case, we can take arbitrary, if we take V, that is element of our algebra omega, we may try to understand what is probability of our event uj under the condition that V happens. So what we know, what we have to compute. Suppose we want to compute the purposes, we want to compute this conditional probability, knowing this provision, this conditional probabilities. Sorry, this is uj. We shall see that in many cases we have to compute for this particular event the conditional probability when V happens, and we know that opposite conditional probability, the probability of V when we have uj happens. The simplest case is when omega is decomposed in two sets. For example, you can say one set is the set of infected people. The other set is the set of people that are not infected. Of course, you have the composition of your space of all people in two sets. They are complementary. You're infected or you're not infected. So we are asking about the following. For example, what is probability, for example, that a guy that at the beginning may be infected or non-infected, but let us say, what is the probability after 1 month to be in the hospital with, how to say, infected, but also with fever and very bad state. Therefore, we can say, if the guy already is infected, that probability to go to the hospital is really can be very high, at least for example, some 5–6%. Instead, at the beginning, he is not infected, probability that after some period he is in hospital is slightly smaller. And then you see, you have such type of conditional probabilities. But this means that the event V to be in the hospital is in some sense subordinated to know if the guy is with virus 1 month before or without a virus. So if he is infected or not infected. And this is that really we want to compute, and we shall see that we have the following formula of the Bayes. I shall write it, then we shall make a small break, and after the break we shall prove it. So when you compute probability of event uj, this is exactly equal to the probability of V when you are in uj. Then you multiply by probability of uj, and in denominator you have to take the sum of probabilities of same V under u kappa times probability of u kappa, kappa from 1 to n. Remember that this n is total number of subsets that measures how many elements we have in our decomposition of the total set. So the formula that we shall prove after the small break, and we shall try to prove, and then we shall make an example. This is the famous formula of the Bayes. This practically says, if we know all these probabilities, but according to our division u kappa, when u kappa happens, we know probability of V, then we can compute the probability that uj happens, provided V occurs. So this is our purpose, and we can make now very short break. I prefer to make these breaks not like before to be 1 big hour and then break. I know that today is very heavy day for you. Therefore, let us stop the registration, make a small break, and after 5 minutes, we can continue. Of course,